Hi everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements, and this is the fourth in a series of videos entitled FEA101, which is an introduction to the finite element method and finite element analysis for new users. So in this video we're going to be talking about interpolation functions, which are a very important part of FEA. So just a quick overview of what we're going to look at today. We're going to have a quick return to video number 1 where we mentioned interpolation functions and mentioned how important they were. We're going to quickly go back over one of the slides from that video. We're then going to talk about, well, what exactly is interpolation. We're going to talk about different types of polynomial functions that are used for interpolation. We'll then look in detail at interpolation in one dimension to give us a good understanding of how it works. We'll look at linear and quadratic interpolation functions and some applications of those as well. We'll then talk about expressing interpolation functions in different coordinate systems, which is very important again for finite element analysis. And then we'll go on and talk about the Lagrange interpolation functions, some applications of those. And then finally we'll quickly cover some other interpolation functions that we'll come across in the rest of this series later on when we look at more complicated finite elements, particularly the Serendipity and the Hermite interpolation functions. So first of all, as I mentioned, we're going to go back to video number 1 and just go back over our definition of what FEA and finite element analysis actually is. Well, you might recall back in video number 1 we said the finite element method divides the domain of interest into smaller subdomains called finite elements, and the solution of the governing partial differential equations is approximated by a simple polynomial function in each element. This term here, the simple polynomial function, this is the interpolation function which we're going to be talking about in this video. So the mention of the interpolation function as a polynomial function comes in the first bullet point here in this slide. But again, if we just work our way down through the description of the finite element method, these polynomials may then be pieced together to give an approximate solution over the entire domain or the entire problem. And at this stage, a variational integral is used to evaluate the sum of the contributions from each element to give an optimal value at each node. And the end result of this is to produce a set of simultaneous algebraic equations for the unknown values at the nodes. We can solve these equations by applying boundary conditions and initial conditions to get a list of the unknown value at each node. And then very importantly, the same simple polynomial function, which in our case is the interpolation function that we use at the beginning of the process, can then be used again to find the unknown value at any point in the domain. In other words, not just at the nodes. So here in the previous bullet point we say, well, the FEM method solves the problem by finding the unknown variable at the nodes. Here we can reuse the interpolation functions to find the value at any point, not just the nodes. So again, the important thing here is the polynomial function is appearing at both the start of the process and again at the end of the process. So interpolation functions are very important in FEA. And again, interpolation functions, as I mentioned before, are also known as shape functions. So let's just start with a quick overview of interpolation. What is interpolation? What does it mean? Well, we're going to start off by looking at this problem here where we have two measurements. So essentially we have a length along a line here, and we've got vertical displacement measured at 2 points along that line. So first of all here, interpolation is a method of estimating a value between two known values in a sequence of values. So for example, consider the two data points shown in the figure I and j here. So we know that at 2 meters along the line we have vertical displacement of 0.1 meters, and at 4 meters along the line we have a vertical displacement of 0.15. But that's all we know. We haven't got any data in here. So suppose we're asked then, well, what is the vertical displacement of the point P, which is 2.5 meters along the line? So again, it's in here. So P is around there. So what's the vertical displacement of P? Well, we don't have a measurement at that point. But we have measurements at points either side of the point that we're interested in. So P is between the known points I and j, so we must make some kind of assumption as to how the vertical displacement varies between the points I and j. And we usually assume that a polynomial function can be used to describe how the vertical displacement varies between two known points. So often, in a very simple way, we'll draw a line between I and j, but by drawing that line, we're basically assuming a linear polynomial function or a first order polynomial function. So Polynomial functions then will generally have this form here, where we have a set of constants and different orders of x. So a polynomial function of order n will start off with the n constant multiplied by x to the power of n, and followed by n minus 1, n minus 2, all the way down to x to the power of 0. So let's take a look at some examples, some simple examples. The most obvious one is a linear polynomial. And in a linear polynomial, we have, it's a first order polynomial equation. So essentially the highest order of n is 1. So we have a1x to the power of 1 plus a0x to the power of 0. Again, x to the power of 0 is 1, so we can rewrite that as a1x plus a0. And that describes a line. If we draw it on the Cartesian plane, the xy plane. So for example, we have this line here, which is the function described by 2x plus 1. So in that case, the a1 constant is 2 and the a0 constant is 1. Next thing we can have then is a quadratic polynomial, or a polynomial of order 2. In this case, we're going to have, it's going to take the form a2 times x to the power 2 plus a1 times x plus a0. And again, we've got various examples here. So for example, we have x squared plus x plus 5, where the a1 constant is 1, the a2 constant is 1, the a1 constant is 1, and the a0 constant is 5. And we get this curve here. And we can keep on going, and we can get a cubic polynomial, or polynomial of order 3. So again, the highest power of x is 3, third order polynomial. And we've got various examples of that as well. So generally speaking, a linear or first order polynomial describes a line, a quadratic polynomial describes a singly curved curve, and a cubic polynomial describes a doubly curved curve, or a curve with two turning points on it. So again, this is something we're probably very familiar with before coming to this video, but just covering for completeness. So if we go back to our original problem then again, where we were told that we had two measurements of vertical displacement along a line. So we'd one at 2 meters and we one at 4 meters. But then we wanted to find out, well, what is the vertical displacement at 2.5 meters? So generally what we'll do is we'll draw a line between the points I and j, or assume a linear polynomial, or assume a first order polynomial. So interpolation function between I and j. And in this case, the function would be of the order here. So v is vertical displacement, and we have a constant times x plus a second constant. And again, just to be very clear, that is coming from our previous slide here, where we have this first order polynomial of this form here, where we have a constant times x plus a second constant. Here we have a constant times x plus a second constant. So it's again a first order polynomial. So by looking at that polynomial then, we can say, well, that's describing the interpolation between these two, but we know certain values. So we know at the point I that x is going to be equal to 2 and that v is going to be equal to 0.1. So we could say, well, vi is going to be c1 xi plus c2. So in other words, we're going to have a constant c1 and c2, but we're going to know that xi is 2 and vi is going to be 0.1. And the same at the point j, we're going to know, well, we're going to know the vertical displacement of j is 0.15, and we're going to know that the coordinate of j is 4 meters. So we can put our known values in there, if you like. So we can rearrange these equations and find out that c1 is simply vj minus vi over xj minus xi, and c2 is various combinations of vi, vj, xj, and xi, which again are all things that we know. Now clearly from looking at this, it's very obvious that, you know, from anyone who studied polynomial equations before, that c1 is going to be the slope of the line, and c2 is going to be the intercept with the y-axis. But in many cases, we don't have time to figure this out when we're interpolating between these two values. So actually expressing c1 and c2 in terms of known values is much more efficient for us. So what we can then do is, once we've worked out c1 and c2, we can put them back into our original equation. And now we have an equation which has vertical displacement on one side, length along the line here, and various combinations of the known points in here. Now what we can do then is rejig this equation a bit and group some like terms together. By doing that, we end up getting, well, the vertical displacement along at any point along the line is given by VI, which is the vertical displacement at one end, plus VJ, which is the vertical displacement at the other end, and various combinations of XJ and XI in the bracket terms here. So again, just to reiterate, we will know everything in here except for X. Okay, and X is what we're trying to find out. So in this case, we're trying to find out the vertical displacement at the X coordinate 2.5. So we will put all the information we know, xj, xi, vi, and vj in here. Then we would set x equal to 2.5, and this will give us the vertical displacement at the point 2.5 according to a linear interpolation between the points I and j. So again, if we actually put those values in this case, and just check out and see how this works, we're going to put in xj is 4, x is the point we're looking at, which is 2.5. Again, xj is 4, xi is 2, and similarly on the other side here, put all those values in here, work that out, and we end up finding, well, the vertical displacement of the point P is 0.1125 meters. So again, if I has 0.1 and J has 0.15, we're saying that P has 0.1125, which would make sense because it's between these two values and a little bit closer to I than it is to J. So from our previous slide, we essentially had this equation here. And what we can do is we can notice, well, this is of this form here, which says that the vertical displacement of any point is SI VI plus SJ VJ. And the functions SI and SJ are known as the interpolation functions or shape functions. And as we've seen, they relate the unknown value, which in our case is displacement, of any point on a line to the known values, which in this case was vertical displacement at the either end of the line. And one of the first things then we can notice about these shape functions, so just to explicitly state that these are our shape functions or interpolation functions, SI and SJ, that we've just worked out. And one of the first things we can note about them is that, well, each shape function has a value of 1 at its own node, or its own point, and a value of 0 at the other point. So for example, SI, the interpolation function or shape function SI, which is here, if we put in a value of xi for x, we will get a value of 1 here, because we'll have xj minus xi divided by xj minus xi, which is basically this 1 over 1. And then if we put in a value of xj here, we get xj minus xj, which is 0. So we get a value of 0. So the shape function or interpolation function varies from 1 at its own point down to 0 at the other point. And the converse goes for j then here. It goes from 0 at point I to 1 at point j. So this is known as the Kronkner delta property, and it's very, very important for interpolation functions or shape functions in finite element analysis. So you'll find that we're always going to be setting up our shape functions so that they exhibit this Kronkner delta property. And we'll talk about that later on, why that is so important. The other thing that we notice is that any point between I and j, so between the points we're interpolating, that SI and SJ will be equal to 1. So again, if we take a look at point I here, SI is 1, SJ is 0, so 1 plus 0 is 1. Similarly at J, SI is 0 and SJ is 1, so we get 1. Halfway in between, SI is 0.5, SJ is 0.5, so they always add up to 1. Any point in there, they must add up to 1. So let's just try and bring what we just said there and bring it into kind of some kind of physical reality and look at some kind of a realistic example and just show how that would work. So in this case, we're going to look at linear displacement of a bar. So we have a bar that's rigidly fixed at its left-hand edge, so it's fixed to a rigid wall, and there's a force applied to its right-hand edge. And we're going to assume this is a one-dimensional truss problem, so we're going to say there's no gravity here, that all the forces and reactions are in the horizontal direction here. So let's look at this idealization of that problem here. So we have a cross-section to the bar problem. In this case, we've designated the rigid wall here, the origin of our coordinate x. So x is equal to 0 at the wall here. And then we're going to say at the end of the bar, we have x is equal to L. Okay, so we have a bar of length L. X starts at the origin here, and it has L at the tip of the bar here. So if we were to conduct some experiments and with this bar set up and measure horizontal displacement, we're going to give this symbol U at different points along the bar. Suppose we set up a grid on the bar and we measured how much it deformed due to the applied force. We'd find something like this. We'd probably get some kind of a curve like this. So let's go and see how we'll deal with that. So now we're going to consider a small segment of the bar. Let's say it's midway along the bar length, and we're going to say the segment is between two points in the bar, and we're going to call them I and j. So at this location here, we have our coordinate x is equal to xi, and at this point here, we have our coordinate x is equal to xj. And the displacement of these points would be somewhere on the previous graph we've shown. So, if this is xi and xj, we're going to be looking at the points P and Q in the graph we've shown, and at the point xi we'll have a displacement ui, and at the point xj we'll have a displacement uj. Now we don't know the function that describes this curve. Okay, it's curved. It could be a quadratic function, could be a cubic function. We're not given enough information to do it. So at the moment, what we're going to do is we're going to just assume that a linear interpolation between P and Q will suffice. Now, obviously, that's not going to be correct because it's clear that there's a bit of a curve here between P and Q. But for the purpose of illustration, just this example, we're going to do a linear interpolation between P and Q. So, rewriting our previous equation for our bar form, or for our bar then, so previously we had u is equal to c1x plus c2. Sorry, previously we had v because we were talking about vertical displacement. Now we're talking about the horizontal displacement, so we're going to say u is equal to c1x plus c2. So this bit's as before, we just replaced the v with a u. We have our interpolation functions as before. We're going to say u is equal to siui plus sjuj, and we already worked out that si is this and sj is that. So again, these are just the functions we worked out on the previous slide. One thing then we can notice is, well, xj minus xi is the length of the bar segment that we're considering. So we could just put in L instead of xj minus xi. Okay, and this is giving us equation 314 from the book. So now if we go and look at a specific example of that, so linear displacement of a bar and truss. So now we're told we have a bar segment of length 0.2 meters is subjected to an axial tension that causes it to deform along its length. The displacement of the left-hand edge of the segment was measured at 0.05 meters, and the displacement of the right-hand edge was 0.08 meters. Determine the displacement of the midpoint of the bar segment. So let's look at the solution to this problem. So from the problem statement, we have xi is equal to 0 and xj is equal to 0.2. So a bar segment of 0.2. So we're not told where it is, but we know the length of it, so that's enough. So we can just say, well, one edge is at 0 and the other is at 0.2, and we're just going to use the length of 0.2. And we know that one point deforms 0.05 and the other one deforms 0.08. So we can say ui is 0.05 and uj is 0.08. So at the midpoint of the bar segment, x is going to be 0.1. So it's midway between these two. So we're asked to determine the displacement of the midpoint of the bar segment. So putting this into equation 314, which we just had a second ago, gives us si, we're going to say at x is equal to 0.1, is going to be xj minus the x of the point we're looking at, which is 0.1, divided by the length of the bar segment, which is 0.5. And sj, similarly, is going to give us 0.5. And again, surprise, surprise, we're at the midpoint of the bar segment. The interpolation or shape functions vary between 1 and 0, so they're both going to be 0.5. So then we can put that into our full equation. And again, we're going to say that u at x is equal to 0.5 is going to be si ui. So si comes from there. Ui we were given in the question. Plus sj uj. And fill in all those values and we get a value of 0.065. So again, this makes sense as it's between the two known displacements of the edges of the segment, 0.05 and 0.08. Also note that the shape functions si plus sj is equal to 1 as required by equation 311. So again, 0.5 plus 0.5 is 1, 0.065 is between 0.05 and 0.08. So everything looks logical. Okay, so now let's take a look at a second example. So in this case, the problem is to repeat the previous example, but this time determine the displacement of the point a quarter of the length along the bar segment. So this time, x is equal to 0.05 instead of being equal to 0.1 as it was the last time. So basically everything stays the same, but we just change that value in our shape functions. Okay, and in this case we get SI is 0.75 and SJ is 0.25. And again, we put that back into equation 313 and we get SI UI plus SJ UJ. So the UI and UJ are the same as before. We've changed the SIs because we're looking at a different location. Okay, we calculate the shape functions at the location of interest, or interpolation functions at the location of interest, put them into this equation here, and this time we find out we've got 0.575 meters. Again, this time the displacement is closer in value to that of the left-hand edge of the segment, as the quarter point is closer to the edge, and as usual, our shape functions 0.25 and 0.75 add up to 1. So now we're going to introduce different coordinate systems, and we're going to start off by introducing the global and local coordinate systems. So up to now we have been looking at the global coordinate system. So the global coordinate system is measured from the global origin. So we could have had a bar segment that was far from the global origin, but we would have given it a coordinate based on capital X. So previously we used capital XI and capital XJ for the coordinates for this bar segment here. So you can see we're using capital XI and capital XJ. But we could also have used a local coordinate system. The local coordinate system has its origin in the left-hand most point on the bar segment. So in this case it's given a small x. So the local coordinate system is a small x. And essentially the points here have two coordinates, which is 0 and L, which is the length of the bar segment. So the global coordinate of any point in the element is given by the element's the global coordinate of the first node plus its local coordinate. So using this we can convert between local and global coordinates. So what we can do then is we can re-express the shape functions that we previously worked out, and we can convert them into local coordinates. So previously we had SI in terms of global coordinates here, but putting in capital XI plus small x for capital X, we can rearrange these equations and give us 1 minus x over L and then x over L. So our SI and SJ become 1 minus x over L and x over L. So again, it can be convenient to work in terms of local coordinates instead of global coordinates. And again, we'll come back to why we will need this later. Previously we looked at linear interpolation or first order interpolation between 2 points. Now we're going to look at quadratic interpolation. So essentially the difference here is that in the examples above we used a first order polynomial to describe the variation of the horizontal displacement of the bar between the points I and j. We could alternatively have assumed a second order polynomial to describe this variation, and in such a case we would use a quadratic interpolation function, which would be of this form here. As discussed before, we have c1x squared plus c2x plus c3. So again, u is the vertical displacement of any point along the line, and c1, c2 and c3 are constants. So in order to use quadratic interpolation, we need to interpolate between 3 points. So we produce a third point denoted by k that has the global coordinate of xk and it's midway between the points I and j. So again, previously we would have had xi and xj. Now we have an xk in the middle, and there's a corresponding displacement with that point k as well. So we have ui is equal to c1 xi squared plus c2 xi plus c3. Again, uj deals with xj, and then uk deals with xk. So now we've got 3 of these equations and an extra term, whereas before we would have had 2 of these equations and just 2 terms. So again, we're going to use the same procedure as before, and again we're going to find out, well, the shape functions end up looking like this. So in global coordinates they end up being 2 over L squared and various combinations of xi, xj and xk in global coordinates. We can equally determine them in local coordinates, and in that case they look a bit different. So again, we would literally just put in here for x, we would put in capital Xi plus small x and rearrange the equations to give us the local coordinate form, and these are the shape functions, the quadratic shape functions in local coordinate form. So the next thing we're going to look at then is the Lagrange interpolation functions. So Lagrange interpolation is a more generalized form of interpolation function. It's not specific to quadratic, cubic, etc. So we're going to introduce the Lagrange interpolation as a general method of determining shape functions for any element based on the number of nodes in the element and or the type of interpolation required. So suppose we have an unknown function describing the relationship between element coordinates and element displacement as shown here. So again, this doesn't obviously fit into a linear or a quadratic function. Also, up to now, we've been using I, J, K to simplify the points or the nodes. So for elements with more than 2 or 3 nodes, we can continue going on L, M, N, and so on. But it becomes more convenient for this discussion to actually just start using numbers. So for now, we're going to say, well, the displacement of any point along this curve here can be given by S1U1 plus S2U2 all the way up to SNUN, where S, the various S's are the shape functions or interpolation functions, and the U's are the displacement of those points. So using the Lagrange then interpolation functions, we have this general method, and it's basically given by these equations here. So essentially we have S1 follows this pattern here, S2 follows that pattern there, and if we go on and look at the pattern, our pattern ends up being this here, described by Sn. So Sn is going to be x minus x1. So remember, x is the coordinate of the node 1 or point or node 1, x2 is the coordinate of point or node 2, and so on up to xn, given the n number of points. So again, S1, S2, S3, Sn are polynomials of degree n. So this is all very abstract. This is a definition of the Lagrange interpolation functions, but I think the best way to try and understand them and see how powerful they are is to take a look at an example. So let's look at a very simple example. So our problem is we're considered the 2-node truss element shown in the figure below. So truss means that it can just get longer or shorter in the horizontal direction. Use the Lagrange method to determine the shape functions or interpolation functions for this element. So we're told that node 1 has a local coordinate of 0, node 2 has a local coordinate of L, and it's of length L. So applying the Lagrange using equation 322, which is the one that we're just in the previous slide. So we have S1 is equal to x minus x2 all over x1 minus x2, which is x minus L all over 0 minus L. So again, x2 is the coordinate of node 2, which is L. x1 is the coordinate of node 1, which is 0. X is general coordinate, which we're trying to find out for our shape function. So we're left with 1 minus x over L. And similarly for S2, put in all the values and we get x over L. So notice something familiar here, the same result as before. These are the one-dimensional linear shape functions expressed in local coordinates. Okay, so they're exactly what we got before, expressed in local coordinates. So let's look at another example. So consider now we have a 3-node truss element shown in the figure. Use the Lagrange method to determine the shape functions for this element. So again, we've got node 1 here, node 2 in the middle, node 3 there, and they've got coordinates of 0, L over 2, and L. And again, the element is length L. So again, using the equations we had before, we just put in all our values. Again, we only need to go up to 3. So if we just briefly jump back to the slide where we had the equation, Lagrange equation here. So in the first example there, we only had to go up to 1. In this case, we have to go up to 3 because we have 3 nodes. So here our highest value of x is 3. So we use the Lagrange pattern, the Sn pattern. We get S1 is equal to this, S2 is equal to that, S3 is equal to that. And again, if you go back and look at these are exactly the same as equations 320 in the book, or when we had a couple of pages ago, which are the one-dimensional quadratic shape functions in local coordinates. Again, which makes sense because we have a one-dimensional element with 3 nodes, so that is quadratic interpolation. So the Lagrange is a very convenient way of giving us the shape functions once we know the number of nodes. Without having to derive them from first principles, we can simply use the Lagrange pattern, if you like, and it will give us the equations automatically. So then let's take this a little bit further. So first we're going to consider an imaginary element, and in this case it's 3 nodes, but the second node is not placed at the midpoint of the element, but rather it's placed at 3/4 of the length along the element. Okay, so all the examples we've looked at up to now have had points or nodes at either end and maybe one directly in the middle. This one doesn't. It's got a node at 0, a node at L, and one at 3L over 4. So again, normally it would be quite difficult to derive the interpolation functions for this type of element, but using the Lagrange method, it's very, very simple. Again, we just put in our values. So we're going to use equation 322, and here we are. We use our Lagrange functions again, and we find out that S1 is this, S2 is that, and S3 is that. So again, really, really simple. We just follow the pattern of the Lagrange shape functions. Now we're going to introduce the natural coordinates. So previously we talked about local coordinates and global coordinates, and now we're going to take another look at a different type of coordinate, which is called a natural coordinate. So from our previous discussion, it should be fairly obvious that we need a global coordinate system to represent the location of each node and orientation of each element, and to apply boundary conditions and loads, things like that. And the solution giving nodal displacements is generally represented and more useful in terms of the global coordinate system as well. But on the other hand, we need to employ local and natural coordinates because they can offer certain advantages when we build a model or compute integrals during the solution process. And this advantage becomes readily apparent when the integrals contain products of shape functions. For a one-dimensional element, then, the relationship between a global coordinate and local coordinate we talked about before. And we talked about developing our shape functions in that local coordinate. Natural coordinates then are basically local coordinates in dimensionless form. So we often need to use numerical methods to evaluate integrals for the purpose of calculating element stiffnesses and things like that. And natural coordinates have the convenience of having values of -1 and 1 as the limits of integration. So for example, if we take our same element as we had before here, we have xi and xj being the local coordinates that has a length L, we can establish a natural coordinate system which has its origin in the center of the element and is given a symbol of the Greek letter eta. Okay, so eta is the natural or non-dimensionalized coordinate. And we can set this coordinate system up in such a way so that one node has a coordinate of eta is equal to 1, and the other node has a coordinate of eta is equal to -1. And we have a simple transformation that allows this to happen. So for a 2-node element in one dimension here, a line element essentially, eta is going to be 2x over L minus 1. Okay, so we can convert between x and eta using this transformation equation here. So what that then has the effect of doing is it changes the shape functions into their natural form, which gives us si is a half 1 minus eta and sj is a half 1 plus eta. So these natural linear shape functions have the same properties as linear shape functions as we discussed earlier. And again, our displacement distribution then will be the same as before. So the displacement at any point of the element will be si ui plus sj uj. And again, we just replace si with half 1 minus eta and sj with half 1 plus eta. We can do the same thing for a quadratic element or a 3-node element. In this case, we're going to have one node at eta is equal to 0, one node is equal to 1, and one node is equal to -1. In this case, the transformation between x and eta is a bit more complicated. So because we have the extra node, we need to use this transformation. And we get the shape functions in a different format. And again, the important thing about these shape functions is they're much more easier to remember. They're much simpler. And remember, at the end of the day, we're going to be programming our finite element code. So having interpolation functions that are easier to describe, easier to program, less terms in them, make things, computation a lot quicker and a lot easier. So let's go back to Lagrange again and look at Lagrange interpolation with natural coordinates. So we previously developed the Lagrange shape functions using the local coordinate x, but we could have also used the natural coordinate eta. And again, we really just use exactly the same form, but instead of having x, we're using eta. And the Lagrangian shape functions are very useful as they automatically ensure that the Kronkner delta property for shape functions is satisfied. And let's take a look at this by again picking some kind of arbitrary element. So let's consider a 6-node one-dimensional element. Okay, so we have this element that it's got 6 nodes. and we're going to say that the nodes are at eta is equal to -1, eta is equal to 1, eta is equal to minus 0.75, minus 0.2, minus 0.3, sorry, plus 0.3, plus 0.6. So there are the locations, the eta locations of our 6 nodes. Okay, so if we look at the graph here, we have a eta, and this is eta along the bottom axis here. So we have a node at -1, we have one at 0.75 here, we have one at minus 0.2, which is here, we have one at 0.3, which is there, and we have one at 6, which is here, and we have one at 1, which is there. So again, we have the arrows pointing to the various nodes that we're going to be using here. So a 6-node one-dimensional element, we need a function that will equal 1 at eta is equal to 0.3 and be equal to 0 at all the other designated nodes. Okay, so at eta is equal to 0.3 here, it must be 1. It must be 0 here, it must be 0 here, it must be 0 here, 0 there, and 0 there. So the only way we can do that is to have a function that's going kind of up and down like this. So we basically can use our Lagrange interpolation as before. So here we're saying that we're looking at node 3, and we have a 6-node element, so it's a 5th order equation. So by plugging our values in there, then we can work out very easily what our shape function or interpolation function would be. So we can perform this for any number of points, in other words, nodes at any designated locations. So a Lagrange polynomial of order m at location k is given by this equation here, which is what we essentially had. And our shorthand way of writing this is using this notation here. So the one thing that's important to notice about this here is you would be expecting an eta minus eta k term, because you're going, so for example, we're looking at point k, location k, and we work our way down from eta minus eta 0, eta minus eta 1, blah, 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 all the way down to k minus 1, and then we jump to k plus 1. Okay, so we don't have an eta minus eta k. Okay, we have an eta minus eta k minus 1 and an eta minus k plus 1. And then we go back all the way down to m, and again. So again, you know, that is contained in the equations we had previously, but it's just important to note that. So far as then we've just discussed interpolating along one axis, which is applicable to line elements like trusses and beams, but we can also interpolate in two directions, which is applicable to 2D finite elements like quadrilaterals. If we look at Lagrange interpolation in 2 dimensions, then it's helpful to use Pascal's triangle to give us an overview of the complexity of the interpolation equations. So if we were to take the most easy type of element we can have, which is a 4-node rectangle, okay, that's going to end up having terms in x and y and xy, okay, and we end up with a rectangle with 4 nodes. A polynomial then of degree 2, so is a quadratic, and we're going to end up with mid-side nodes and also a midpoint node, so we end up with a 9-node element, and then similarly on for a 3rd order polynomial. And again, you'll see more and more interaction terms. So this first one here is known as a bilinear quadrilateral because we have this xy term, and again the other ones get more complicated as we go on. So an order n element is going to have n plus 1 squared nodes arranged in a square symmetric pattern, which in general requires internal nodes. Okay, so the first one doesn't have it, the polynomial of degree 1 doesn't, but all the others will have internal nodes. So shape functions are products of the nth order polynomial in each direction. So they're going to be bilinear, which is the first one, biquadratic or bicubic. So a bilinear quad is a Lagrangian element of order n is equal to 1. So it's this one here. So we're going to take a look at this one as being the simplest one, just in this introductory lecture on or talk on interpolation. Later on we'll talk more about getting into the more complicated ones, but for now we're just going to take a look at this one just to see how the process works, because it's the simplest one available to us. Here is our bilinear quad, or our 4-node quadrilateral element. And again, this is set up in a natural coordinate system again. So previously we had the natural coordinate in the horizontal direction, which was eta. We now have a natural coordinate in the vertical direction, which is neta as well. So each of these nodes is set up to have values of eta and neta, which are 1 and minus 1. So for example, node I or point I has an eta of minus 1 and neta of minus 1, whereas k up here has an eta of 1 and a neta is equal to 1. So we have essentially this line has the coordinate of neta minus 1, this is the coordinate of neta plus 1, this is an eta plus 1, and this is an eta minus 1. And again, we can transform between x and y and eta and neta using these equations here. And xc and yc are the coordinates of the center of the element, and a and b are generally the width and height of the element as well. So if we know those values, we can work between x and y and eta and neta. So if we get our displacements then in the two directions, you'll see that we have displacement in the horizontal direction, which is u, and displacement in the vertical direction, which is v. So u is going to be a function of eta or x and neta and y, and it's going to have a constant plus a constant times eta plus a constant times neta plus another constant with eta times neta. And then again, same for v, but there'll be different constants. So again, we have first term is just a constant, second term is eta, third term is neta, and the fourth term is the interaction eta and neta. And if we just briefly jump back to Pascal's triangle again, we replace eta with x and neta with y, we'll see we have first term is a constant, then we have an eta term, or an x term, a neta term, and then an eta neta or interaction term. So again, that's what we have here. These are the bilinear terms, and they imply that all shape functions are products of linear functions of x and y. So if we use the previous procedure now in two directions, so we want to find out the shape functions here. So we know that we're going to use eta and neta. Here's how we convert between x and y and eta and neta. We know our functions are going to be of this form here, but we want to find out what these shape functions are. So if we look in the horizontal direction, first of all, we essentially do what we did before. So we're going to look at node I. So it's a first order polynomial at the point I. So at point I, we're basically again treating this like it was the line like before, and just getting like SI like we would have had before. So in this case, HI, the horizontal component of the shape function, ends up being a half 1 minus eta. We can do the same thing for the vertical direction then, and we can say again we're just interpolating this way, and we're saying that VI first order, so again looking at node I but going in the vertical direction and using a first order equation gives us neta minus neta j all over neta I minus neta j. Again, these are exactly the same as we did in the one-dimensional problems earlier, and this case gives us a half 1 minus neta. So we've got two parts of the shape function, and basically if we multiply them together we get the full shape function. So SI, which is a function of eta and neta, is going to be the horizontal part we just worked out here multiplied by the vertical part we just worked out there, which is a quarter 1 minus eta 1 minus neta, which is the shape function for the bilinear quadrilateral element. And we can do the same things for nodes J, K, and L and work out SJ, SK, and SL as well, and that will give us the shape functions for this element. So the higher order elements more or less follow the same procedure, but again, this part is going to be a bit more complicated because you're going to have second and third order equations and not just first order. I think it's kind of easy to understand it for the first order equations. Once you can get this, you can go ahead and take a look at the second order and third order. The next type of interpolation we're going to look at then is the serendipity interpolation functions. So we're not going to get into the theory of those, but just to briefly mention them at this stage, as we're going to get into later on in this course when we look at quadrilateral elements later on. But essentially the serendipity interpolation functions, again looking at Pascal's triangle, they exclude terms that reside inside this inverted cone here. So the first element, the polynomial of degree 1 element, is still a bilinear quadrilateral element like the one we just looked at. The next one though doesn't have this term here. So it doesn't have the x squared by y squared term. And when you go to the third order one, it doesn't have these four terms here. So In general, we only have boundary nodes, and it avoids the use of internal nodes. They're generally not as accurate as Lagrangian elements, but they're more efficient and they avoid certain types of instabilities. So you'll find that most of the two-dimensional finite elements that are used in most commercial packages these days are using the serendipity interpolation functions. So as I said, we will talk about these later on in this course, but for now, just to be aware that this is what the serendipity interpolation functions look like. This is the kind of elements they produce. And then finally, we're going to look at Hermite interpolation functions. So the Lagrange interpolation functions are suitable for the interpolation of a dependent variable, which in our case is displacement, and they ensure continuity of this variable across element boundaries. However, in some cases, we need to ensure continuity of both the dependent variable and its derivative across element boundaries. And the most obvious example of this is something like beam bending, where we use the Euler-Bernoulli beam bending equations. We must ensure continuity of the dependent variable, which is vertical displacement, and its derivative, which is slope. So in that case, we're looking at, let's say, a beam element that looks like this, that again has a node I and a node j. We don't just have vertical displacement, we also have a theta I and a theta j, which is the slope or rotation, if you like, of these nodes. And again, if you look at the Euler-Bernoulli beam equations, you can see that we have this, second derivative of vertical displacement here, and we have slope being essentially the first derivative of vertical displacement. So again, we'll need to take those derivatives into account in our shape functions. So if we look at the Hermite shape functions, you'll see that we have 4 of them. Okay, so we have an SI and an SI theta and an SJ and an SJ theta. So one shape function is describing the vertical displacement, and the other shape function is basically describing the change in slope. Okay, and you'll see that again they have the same properties. So SI has a value of 1 at its own node and a value of 0 at the other node, and it has a value of -1. Sorry, SJ has a value of 1 at its own node and a value of 0 at the other node. So again, this across the bottom here is natural coordinate. Okay, so 0 in the middle of the element, 1 at node J, -1 at node I. And again, SI plus SJ is equal to 1 at any point through the element. If we look at SI theta and SJ theta, SI theta has a slope of 1 at node I and a slope of 0. In other words, it's flat when it gets to node J. And then SJ theta is the opposite, so it has a slope of 0 at node I, and it has a slope of 1 as it approaches node J. And again, the only way you can make that happen is to actually have SJ theta to be mostly negative. So it starts off with a 0 slope, it goes down, and the only way it can be sloping, with a slope of 1 being positive when it gets here, is it for it to be rising. Again, so slope of 1 is rising up like that. So it has to be negative before it gets to that point. And again, these are the Hermite shape functions. And again, the vertical displacement or the displacement of any point along the beam is given by SI VI plus SI theta theta I plus SJ VJ plus SJ theta J plus theta J. And we look at these functions in more detail when we look at beams later on in this course. But again, for the moment, just to be aware, they're a type of interpolation as well that we're going to look at. So let's just have a review then of this video. So what did we look at? We looked about, well, what is interpolation? We talked about different types of interpolation, linear and quadratic interpolation. We introduced different coordinate systems, global, local and natural coordinate systems. We looked at Lagrange interpolation in both 1D and 2D. We briefly then introduced the serendipity interpolation functions and the types of elements that use that. And then we talked briefly at the end about the Hermite interpolation functions and how they're used for beam problems, which again we'll be discussing in more detail later on in this course. So that's it for this quick introduction to interpolation. So again, as always, there's always more information in the book. There's more examples in the book. So if you want to find out more information, please do go and get yourself a copy of the book. I hope you found this video useful, and I will see you in the next part of this FEA 101 course.